you start with having the curve, okay, the curve here, the curve of the function, and then you have the bound, like from A to B, you have the region, rotate the region about the axis of revolution. For this figure, it rotates about the x or the y-axis or the x equals 0 line, and it forms the solid as you see here. To find the volume by shells, this time instead of making a partition or the cross section perpendicular to the axis of revolution, the cross section gonna be parallel to the axis of revolution. Like this is the axis, and you do the cross section parallel to the axis. And then when you perform the rotation, the slice that parallel gonna be acting like it's wrapping around the axis of revolution. Okay, once you see one shell or one piece that wrap around, you take this piece out, we call one shell. If you take one shell out, it will be um the piece that you're gonna um work on finding the volume. As you have this piece and you cut it up and expand them, like unfold them. Okay, I'm gonna go to another piece here. We have the axis of revolution, we have the cross section, we wrap around, it becomes, it performs a one shell for one cross section. And that shell, when you cut it up, you you unfold it, and it just show you as the rectangle piece with the thickness or the rectangular shape. Okay, so to find the volume of one shell based on this idea, you're gonna use the cross-sectional area, which is what the area of the rectangle multiplied by the thickness. The thickness depends on how do you perform the cross-section. And for this problem, the cross-section is, if you lay the position in x, so that means the cross-section has the thickness at delta x or the dx, because when you move the cross section, you're gonna move along the x direction, Now, to find the area, which is the length times width, the length of this rectangle times the height of this rectangle. The height is the function value or the height of the bar that you perform from the original graph, and the length, which is the circumference of the circle, of this circle. And how to find the circumference is 2 pi r. The formula 2 times pi times r. What do you need to know? What is the r? And how do you find r? R is the measurement from the axis of revolution to the bar. So that's the radius. Because the axis of revolution will be right in the center of the figure. Okay, so overall for the shell technique, you're gonna need the thickness of the shell. That means when you perform the revolution, you sketch the graph, you identify the region bounded by those graphs, you rotate about the axis of revolution, and when you pretend like you have one partition or one slice, the slice is parallel to the axis of revolution. The position of the slice gonna tell you whether in the x way or in the y way. If in the x way, that means the slice gonna move along the x direction. The thickness gonna be the delta x. Okay. After you identify either in the x way or the y way, that's gonna tell you to locate the interval of integration. Then you look for the height of the shell and the radius of the shell. Again, the radius of the shell, you perform it by, you find it by measuring the distance from the axis of revolution to the shell. Okay. After you get these four pieces, you put them all to set up the volume in the integration form. So 2 pi r, so that's the circumference, and multiplied by the height of the shell, and multiplied by the thickness. So this one is the thickness. And that is the indicator that you do with respect to x or with respect to y. Okay, if with respect to x, the integrand function has to be totally in x. If you do with respect to y, or the thickness is dy, the integrand function has to be totally in y form. And this is another example, like you can think about, you have the donut, and donut is formed by rotating the region here about the axis of revolution. And then to find the volume of this, you just make like, or you use the cutting to make it like cylindrical shell, and you find the volume of each shell. You have many of them. You put them all together to form back the whole piece of the end of the donut, something like that.